Is it here? Okay. 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 Woohoo. Okay. So woohoo. So I'm gonna. My voice is going. Well, I can do it. Sorry. I'm just like. Whoa! See? All right. Excellent. Okay. So, thank you. I mean, if you do it, I figured it'll make it so you, okay, so let's do lecture in a minute, okay? This is everything you will know at the end, or not necessarily. Learning is iterative. You have to do the homework and blah, blah, blah. For you to know it means you have to absorb it over all the things we do, which is lecture, notes, or book, homework, and discussion, okay? But these are like the central points of what we're going to learn today. So FFT wrap-up is, you already saw this. This should be fairly familiar. What's the idea of the FFT algorithm? Hey. Okay. So what's the idea of the FFT algorithm is it's really, FFT is, we think of it as evaluating a polynomial on a lot of points. That's the task. Because that's useful, because now if you could evaluate polynomials on many points, you can multiply them very easily. You just multiply them point-wise, right? And so that was useful. Now, what's the idea of the algorithm is we're evaluating a degree n polynomial on n points. That is what an FFT sort of is. And the way we do it is we sort of split the polynomial into two polynomials, the odd degree, the odd coefficients and the even coefficients. We sort of evaluate those 2 points, two polynomials on the squares of the points, right? And then which points do we use? We use these nth root of unity. And these nth root of unities have this remarkable property that the squares of the nth roots of unity are the n over 2th roots of unity. So the squares of these points, instead of there being n points, right? So if you had 1, 2, 3 and you squared them, you'd have 1, 4, 9. You have 3 points. You have 3 points and 3 squared. But these roots of unity are really cool. Like if you take -1 and 1, if you start with those 2 points and you square them, you get 1. So from 2 points, you get 1. And this continues if you use complex numbers. You can have complex roots of unity and get 2 to the k roots of unity. They have to be powers of 2. But when you square them, instead of there being n different points, there's only n over 2 points. So that says you can recursively build an FFT using 2 calls on a subroutine that evaluates a polynomial, a degree n over 2 polynomial, on n over 2 points. Okay? And that's the idea. You get this recurrence, and it's victorious and spectacular and amazing, right? And so today we're going to talk about graphs and the representation. You've seen some of this before, so I might go fairly quickly. We're just going to throw in a little bit about asymptotically what the benefits of these kind of representations are. And then we're going to do a procedure. How do you explore a graph? It's sort of the beginning of depth first search. Okay? And in particular, the major data structure used by this procedure is a stack. Okay? And we'll see that. Okay. Okay. And now when you do the runtime analysis for here, you don't use recurrences in general when you talk about graph algorithms. So I'm going to point out I'm going to show you how to do runtime analysis in this context. Okay? Okay, so the fast Fourier transform is, here's the idea. You can rewrite this polynomial evaluation where you put an x in this way, where you have the odd and even degree polynomials, right? You can evaluate this. I talked to Professor Raghavendra, and he said he didn't prove this. I'll do a quick sketch of a proof of this. He asked me to, but it's just algebra. It's not super interesting. It's easy to verify. Okay, and then there's the roots of unity, and so there's some power of 2. We assume n is a power of 2, and the points are going to be 1, omega squared, all these powers of this particular primitive root of unity. But why didn't I write this is omega to the 1? What is this? Omega to the 0. Right? 1 is omega to the 0. When you take something to the 0th power, you always get 1. Okay, so, and this is where W is a primitive, it's a solution to this equation, where primitive means it's sort of the smallest non-trivial solution. Okay? Okay, so here's this algebra that verifies this. Here's a to x, and here I just changed the variable name to y almost everywhere. I missed one. But you see, the odd degree coefficient, like the coefficient of the linear term is a2, where a2 was the coefficient of the power of the quadratic power in the first polynomial in a of x. Okay, and so on. So now what you need to reconstruct a of x is, let's think about a term of a of x. A of x, the power of x, the dth power of x, has the coefficient a sub d. So when you do this expression, if you want to say these two are equal, when you do this expression, you like to say if you think about the coefficient of x to the d in this when you evaluate this thing with x as a variable, you get back a d x to the d, right? And then you term by term you will know that the left-hand side is equal to the right-hand side at the top of the slide. A of x is equal to ae of x squared plus x times a odd of x squared. Okay, so we just break it into two cases. So d over 2 is even. So the d over 2, d is even. So the d over 2th coefficient of ae of y is a to sub d. So that's right. The second coefficient here has x to the 1. Okay, or y to the 1 it should be. But a fourth has y squared. A 2d has y to the d. Okay. Okay, so now you just plug in. And now let's look. That's where we're finding the coefficient AD. We see AD. We plug it into this y. We go AD y to the half as much. And then what you get then is you get AD. And now we're plugging in x squared, right, into here. AD is x squared. And now when you square it, you get x to the d. Okay? So AD x to the d comes from this term, right? When d is even. And similarly for the odd, you have to do something a little bit more. You have to take one extra step. But let's think of where, if a d is odd, all the odd coefficients are somewhere in a odd. This should be a odd. Okay? And then, so you plug it in, y equals x squared, a odd, I'll fix that, of y, contains a to the d y to the d minus 1 over 2. Which is a to the d times x to the d minus 1. So this is not what we wanted. We want a to the d x to the d. But if you see in this expression, then we multiply by x. Right? So we have that x times ae x squared contains a to the d x to the d minus 1 times x. Okay. Okay, so that's just a verification. It's nasty. It's just algebra. You just sort of think about it and figure it out, term by term. Okay, term by term, meaning every coefficient of x to the d. Okay, now complex numbers. Okay, so I looked at the K through 12 curriculum. I see you know them well. Okay. Okay, there's the coordinate representation, which is a plus b times I, where I is the square root of 1, and we also talked about it. Okay, so it looks something like this. You could also represent it in polar form. Here's one form. It's just, you think of a complex plane where the x-axis corresponds to the real part, A, and the y-axis corresponds to the imaginary part, B, A plus BI. You could also write it in polar form where you can translate back and forth to this other representation where r is equal to the square root of a squared plus b squared, and this angle from the x-axis, which is theta, which is tan inverse of b over a. Okay? So now you can do, now what if you wanted to multiply two complex numbers? So you could do this. So now what we say is we also have this notion that this complex number is really R1 is R1 times e to the I theta 1. That's de Moivre's theorem. Okay? And so once we see it like that, we just see that multiplying these numbers is like you just use the rules as if those are real numbers, right? And I theta 1 is in the exponent, and I theta 2 is in the exponent. Okay? And so then you add the exponents. You multiply the magnitude, which is what R is called, and you add the angles. Okay? That's just a way to do it. And there's some cool things, right? So this is what is going to be the new one. It kind of rotates around and scales, right? The multiplication of complex numbers. It's magic. It's a bit of a magic, but it's easy to verify. Okay? And one thing that's noticeable is that if you multiply by e to the pi I, what are you multiplying the number by? Well, it says right here. Okay, it's a negative 1, right? So if I multiply something by e to the pi I, say I multiplied this by e to the pi I, what will the vector look like? Point down here, right? Right? Does that make sense? It rotates it by pi. Right? So that's also, it all makes sense, even from intuition, right? You can say, well, when I multiply by negative 1, which is, in this representation, 1 pi, I actually do rotate the thing by 180 degrees, as you would expect. Okay? But you could also do the algebra, but this gets you intuition as to what's happening. All right? Okay, so now what are the nth complex roots of unity? Okay, there what we do is we can see that, okay, if I use the angle 2 pi over n, okay, the magnitude is 1, right? Okay, so that's the radius. And the angle away from the x-axis is 2 to the pi over n. Now, if you take to the nth power, what we just saw is, well, every time you multiply something, you add the angles. So if you multiply these things by that thing n times, you're going to multiply the angle by n. Okay? So then that's what the second expression there is. And then you say, well, okay, you can all multiply, right? And then you get back 2 pi. 2 pi over n times n is 2 pi. So 1 comma 2 pi is a vector along this direction. So I should have drawn it. It's in this direction. It's 1. Right? 2 pi and 0 are the same angle. Okay? Okay, so now you can do this. You can see the whole thing. And you can do, that was the primitive root of unity, but this is also a root of unity, 4 pi, because if you take that to the nth power, you get 1 4 pi, which is also 1. So all of these are roots of unity, right? And roots of unity. If you raise them to the nth power, you'll get 1. Okay? And you get this picture. Now, what's the fancy thing that we used in the FFT? We used the fact that now, if we square all of these, we get half as many numbers. If we square all these numbers that correspond to these blue points, we'll get half as many points. Right? That's why the FFT works. Okay? So let me verify that. Okay, so you want to pair with the common square. You know, that rhymes. Okay, that's about the limit of how good my poems get. But pair with the common square, right? So I want 2 of the blue things that have the same squared value. Right? That's what I want to show. Okay? Well, it's clear. This one, what is the squared value? Well, that means you multiply this angle by 2. Right? So you would get that red number. Right? And now what about this one? What about pi over, the opposite one? Well, this is just this number times negative 1. So if this number squared is this red number, this number squared is going to be the same thing, right? Because negative 1 squared is what? 1. Okay? So that's one way to see it, but you can see that these two, when you square them, you get that, right? Because you get n, you get 2 times this, which would get 4 pi over n times 2 pi. What does adding 2 pi do? It takes it back to the same thing. Okay? Okay, so that now you see these boxed ones. How many of those are there compared to the blue ones? 10 times as many? Half as many. That's the point, right? So now you could evaluate on way fewer points. Okay, so next is we're going to talk about graphs and reachability. Any questions about FFT? Okay. Okay, this is a weird, odd-shaped country which has sort of very angular states. And the key here is I wanted to color all the states that are next to each other a different color. So did you see that? How many colors did I use here? I used 4. It's a little hard to tell. This one down here is like cyan or something. I don't know. And the red one that's red on the upper left. Okay, I apologize. So what you want to do is then model this problem. I'm going to model this problem. And what I'm going to do is I'm going to create these things which we'll call vertices for each state. And then what I'll do is I'll draw a link or a connection between them if they have a common border. Okay? So these are the ones that have a common border. Here you can tell that the one colored blue on the lower left and the one colored red on the upper right are not touching each other. Do you see that? The blue is not touching the red. Okay, so right now I use 4 colors. Can I use fewer colors to color this map? Okay, so so I can. Do you see what I could turn the blue one to red or the red one to blue? Because they're not touching each other. Okay? Yes, I can do 3 colors. I guess I turned the red one to blue. Does that make sense? Okay, so now I can add this other crazy country, and I colored it red just to use a new color now that I have red available. So I could draw the corresponding graph, which is these vertices, and this pairs of vertices, which are edges. Those are the black things. Okay? And so, and then I could do another one. How about this one? Can I use fewer colors here? I'm using 4 colors here. There's a weird blood red and red. Okay? You see the 4 colors? Can I do fewer? Yeah, I did it. Yeah, you can just color these two the same. So the question now, can I always color a map with 3 colors? Okay? That's one question. When you just start doing this playing around, you should be thinking, right? And saying, oh, what's he doing? This is kind of a puzzle. Let's think about it a little bit. Let's put it in this country, which is, the state. Okay? So now that state touches these 4 countries. Okay, so now I'm using 4 colors again. When I put in a new guy and I color them differently, I know my coloring will be valid because I used a new color. But now the question is, can I reduce the number of colors here? What do you think? Yeah, people probably guessed or they saw. You can't use fewer colors. And this is why. Here's 4 countries. And it's hard to see over here in the country representation, but it's sort of easy to see here. Right? All of those vertices have an edge to every other person, every other vertice in this set of 4. So they all touch each other, so you need at least 4 different colors. Okay? So 4 colors are required. So it's just a little fun. So the theorems, there's a theorem that says for a map, 4 colors are enough. We covered the 5-color theorem, at least when I teach 70. I covered that. It inspires fear and admiration. But the 4 colors it inspires. That theorem is way harder. Okay, so I don't know. Anyway, but it's done. Okay, so here's an example of an application. Who cares about coloring maps? Coloring maps are fine, but a lot of people take 61A and 70 together. A lot of people take 61B and C together. Maybe, I don't know why. A lot of people take 61B and 70 together. 61C and 70. That's also common. These are also common. But usually you don't take 170 and 61A together, right? So, in some sense, what we want to do now is we want to schedule the exams so that we minimize the conflicts. Okay, so here that's a coloring problem. Here there's 5 courses, and we want to have as few there's only the exam slots as possible. So you can color this graph using this coloring. I think, right. So there's a coloring of the graph, right? 70 and 170, if you're taking them together, that's interesting. But but okay, I understand. It happens. But okay, it's above a certain threshold number of people or fraction of the class or something. So you can do this with 3 exam slots and obey all these links. No two courses that are connected by an edge have the same color or have the same exam slot. So it's useful. Yeah, there's all kinds of useful. So your graphs. This is how Unix. There's this operating system called Unix. There's another version called Linux. You should use that and throw away the rest. But this is how it developed up to 93. The chemical networks. These are chemicals. This tells you how they're all interacting. These graphs are everywhere. Okay. So let's think about implementations. How do you implement it? For us, there's this notion. There's a set of vertices and a set of edges. The edges are pairs of vertices. Okay. And you can represent pairs of things in a matrix, right? Where you have what we're doing here is we're writing down which in this matrix the first row corresponds to node 0. Okay, and the ones correspond to the nodes it's connected to. So it is connected to nodes 1. 0 is connected to 1. That's why the first the 1 in the second column of the first row corresponds to this connection between 0 and 1. Okay? Right, this connection corresponds to this one. This connection corresponds to this one, and this edge corresponds to this one. Okay? So this is the set. This is just in set notation what our graph is, right? We have 5 vertices. We have a set of vertices, V. We will always use V as a set of vertices, and E as a set of edges. Okay? And here, this notation here says that 0 and 1, there's an edge between that, 0 and 2, and 0 and 5. Okay, again, that corresponds to the first row in the matrix representation. Okay, you could also represent this as a set of adjacency lists. Okay, you can say, look, vertex 1, vertex 0 is connected has an edge to node 1, vertex 1, and vertex 2, and vertex 5. Okay, I interchange node and vertex often in my language, so just, if you get confused, ask. Okay, node 1, vertex 1 is connected to vertex 0, 2, 3, 4, and 5. Okay? So these are 2 different representations. Okay, so, they have different complexities, right? So for the matrix form, if I want to ask if the edge UV is in the graph, it's really fast. I just look up the right entry in the matrix. I'll look up the uth row and the vth column, A sub v UV. And I can immediately figure out whether this edge is there. So it's very fast to query an edge. Okay? But the adjacency list, if I want to see that node 1 is node 1 connected to node 5, what I might do is look up node 1, look at its adjacency list, and start scanning over the adjacency list. And now if it's connected, for example, to everybody, you may not find 5 until much later. Okay? So the naive usage of adjacency lists will take you longer to answer this query, is this edge in the graph? Okay? On the other hand, for most graph algorithms, you want all the nodes that something's connected to, so it doesn't cost that much. That's why it's in blue. And you could also use something called a hash table or a dictionary in Python and do this faster. But let's just say the simple data structure, it takes longer. Okay, so now if I want all the neighbors of U, for the matrix, what you need to do is you need to scan over the row and say where the ones are. So it takes a long time. The adjacency list, you can almost immediately return the list and just look at the elements of the list. So it's this O of D, where by D I'm saying it's a degree of the vertex, the maximum size of any adjacency list. Okay, and the space is also different. The space for the matrix representation is O of V squared because it's an N by V times V matrix. Here it's order E, right, the number of edges. It should be order V plus E because maybe some vertices aren't connected to anybody. Okay? So this is like the basics. I think you've seen both of these in 61B. Did people see both of these in the 61B when you worked with graphs? Yes? Yeah, good. Okay, so let's test your understanding. Okay. Which one is it? C, okay. Yeah, it's only 0 is connected only to 2, so the list of neighbors is 2. Is only has 2 in it. So how many edges? That's easy. Count the number of black lines in the right. Okay, so there's no other options. So the total length of the adjacency list. What's the total length of the adjacency list? Which one is it? What's the total length of the adjacency list? Well, remember, what's the sum of the degrees of a graph and the number of compared to the number of edges? Remember this? And who took 70 with me? Okay, it's like my favorite theorem, right? It says the sum of the degrees, which each adjacency list, each node has its degree number of neighbors in the adjacency list, right? So you sum the degrees. And now what happens to a degree, an edge? How many times do you see it? What does an edge contain? It contains 2 vertices. So that edge, there's going to be an entry in the adjacency list, say edge UV. There will be an entry in the adjacency list for node U, and there will be an entry in the adjacency list for node V. So for each edge, you have 2 entries in all the adjacency lists. So it's C, 2 entries for each edge. Okay? Okay, so that's, we're going to use that argument again. That's why I went over it carefully. Okay? You see edges from both sides. Okay, so there's this guy, Theseus. He had to kill a minotaur, right? I don't know what a minotaur is. Half man, half bull. Is that right? Okay, right. Okay, so in a maze. Okay, this was his job. He got this job somehow. Okay. There's this woman who thought, oh, this guy Theseus, he's pretty cute. And he's got to kill a minotaur. He doesn't seem quite so bright, okay? But she is, okay? So what she did is she gave Theseus a ball of thread and some chalk, okay? Okay. Do people know this story? Who knows this story? Okay. I'm probably butchering it. But so he wants to... and then she told him, look, this is what you have to do, okay? You know, you're listening, right? You're listening, right? Okay, so, he's a little Tatum Channing. Is that a guy? Channing Tatum? Very good looking, not very bright. Okay, so, well, maybe he's bright, but he's so good looking he doesn't have to be bright, all right? You know. Okay. I think I have to edit that out of the recording. Okay, so what he says, look, go in the room, mark an X when you go there. Every time you take a step, mark an X. Okay? But you want to be able to then, but also do this. If you look for each exit, you look through. If it's marked, you don't go there. Say you're here and you can leave the room there. You see there's a mark there. Don't go. Right? You've already been there. Okay? Otherwise, you go in the room, and what you do is you unwind the thread. Okay? I gave you this thread. Stick one end at the entrance, and as you go in, unwind it when you go into that room. Okay? Then you look around the room. You see if the Minotaur's there. And then you mark the room, and then what you do is when you're done and you look at all the exits, if all the exits are marked, the other side of the exit is marked, you go ahead and leave the room, you go backwards. You go back where you came from. Okay? And how do you know where you came from? Because everything might be marked. How do you know where you came from? Well, you start winding the thread up and it sort of pulls you back to the other room. Right? Does that make sense? When you start winding the thread up, what it's going to do is as I wind it up, I'm going to have to go closer, right, and get out of the room, back to where I came from. Okay? Okay, here's a picture. There's Theseus. You can see he's very good looking. And there's the Minotaur. Okay, so there. Okay, my animations are unfortunate. Okay, so the red thing is the thread. He marked it. He marks the red. Okay, look, there's no place to go here, right? So he says, okay, what do I have to do? The algorithm was he just explores, right? But here he has to do something different. He has to wind up the thread. He didn't know where he came from. I mean, he's really not bright. So, okay, so he came back here, goes back here, then he starts heading up here, here again, he goes there, and now he comes down here. Now, this one's interesting. Here, if he hadn't marked this, well, he would always also see, he could see the thread maybe, but say he hadn't marked it, he wouldn't know to not keep going here, right? So the marking is pretty important, okay? So he sees that he was here, so he goes back, and he goes here. Okay, ready? Oh. You feel kind of bad for the Minotaur here. Yeah, okay. So, okay. Oh, whoops, he forgot to mark that part. Okay, so, yeah, okay. Not very bright. Okay, so what is he doing? He's searching, right? He's searching this maze, right? So, he wants to find out he wants to look at everywhere in this maze. So, for computer science, what we're going to think of it is we're going to look at all the reachable, see every room. We're going to look at every room that's reachable from this entrance. That's what we want to do. Okay? We want to look for the Minotaur in each place. Okay, so that's, in some sense, we're just trying to list all the nodes in the graph which are reachable from some place in the graph. Okay? Okay, so here's what we're doing. We're exploring the graph. We just want to say, maybe we want to do something in the rooms. Theseus wanted to kill a Minotaur, but maybe there's something else you want to do with all the nodes that you can reach here, right? So let's say here's the algorithm, and you can see what we're going to do is whenever we explore a room, we're going to set this visited mark to true. So what does this visited mark correspond to with Theseus? The chalk and the X's. Okay? So when you go into a room or when you explore a vertex, you mark it as being visited. Okay? And now what you do is for every edge every edge that has that vertex as one of the endpoints, you then explore the neighbor if it's not been visited. Right? Right? If there's no chalk or not visited, then you go explore that neighbor. Okay? And now, so you go, that's what we're doing. So we set A to visited. We start with exploring A. Okay. And then we do this. The chalk is red. Okay. Okay, so now I mark it, and I go this direction. And then from D, what I do is I look at F. Right? So in this loop here, I set D to be true. And then I look at the adjacent edges. Well, one adjacent edge is C, but I'm not going to look at that one because C is visited. And then also from D, an adjacent vertex is F. So I look at F, and I see it's marked. Okay, so then I can't go anywhere. So now what I do is nothing, right? Out of the loop, I do nothing, right? And so what happens when I fall out and do nothing? Right? Okay, let's try this again. From A, I did this, and then I see that F has not been marked, and I call explore on F. Right? Okay, I do that. And then I call, from F, I see that C is not marked. I call explore on C. Okay, that's what this thing does, the call. And I go to D, and I say, okay, look, there's nobody to call explore on. Both of my neighbors are done. Okay? So what do? What does explore do? It falls off the bottom of the procedure, right? It's over. So where does it go when it's over? It goes back to the previous invocation of explore. This is a stack of explore calls. So this is a stack. So this thread, winding up this thread, is essentially popping this invocation of explore off the stack, off the call stack. You remember environment diagrams and all these things? You remember and love environment diagrams? This is what's happening. Okay? Okay, and then you go back, and then you can see from F, you go back to the call of F, and F only went over C. So it's still in this loop. Right? This is magic. Programs are magic, right? They're really cool. Right? And so I'm in love with them just describing this to you. So then it says, oh, look, I'm somewhere in this loop. I've already explored the edge of the C. Now I want to look at G. I'll explore that. Okay? And so on. And so, and then it goes back to A. It pops off the stack, and then it comes back to the beginning. And now we've colored everybody light blue because that was our goal, to color all the nodes light blue. Okay? Okay. So now there's something else that's kind of cool. There's a couple kind of edges here. There's the ones that I colored red, which form a tree. Right? There's no cycles in the red edges. Right? Because that's exactly what you don't enter a node which you explored. So you only enter each node once. Okay? So that gives you a tree. Okay? And now there's these other blue edges which we're calling back edges. So in some sense, this Explorer has organized your edges into two kinds. The tree edges, this tree which from anywhere you can get to anywhere on the tree, and there's these other edges, the back, which we call back edges. And why are they called back edges? Because this back edge, in this case, goes back to an ancestor in the tree. Okay? So that's sort of the property. It will give you a tree, and it'll give you some of these blue edges, and all the blue edges go between a descendant and an ancestor in the tree. Okay? So it's kind of cool. There's already cool structure here, right? Already there's some structure. I've categorized edges in certain ways, and they can only go they have a certain property. Okay? And we're going to be using these structures and algorithms. Okay. So now it's correctness. What does it mean to be correct? It means that all and only nodes reachable from A are reached by Explorer. Okay? That's what we want. That's what we mean to be correct. That's the property we want. So when you say a program is correct, you have to say what you mean. And here it means that I do visit every node that is reachable from the starting vertex. Okay? Now, what is reachable? Okay, first of all, reachable means there's a path from U to V of edges. Okay? Okay, so when U is visited, only means when U is visited, the stack contains this call stack. Explore, 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 explore. Now, it has this call stack. Each invocation of Explorer corresponds to an edge. So what you have is a sequence of nodes on the stack where the pairs of the nodes are connected by an edge. Right? I only explore somebody with whom I'm connected by an edge. Okay? So the stack, every node on the stack is connected to the next node by an edge, because that's how Explorer is invoked. Right? That's what it says here. In this line here, line 2, for each edge. So I only do a recursive call on the Explorer if there's an edge. Okay? So it says a stack, all the nodes on the stack form a path. The first node on the stack is the first guy you called Explorer on, and so therefore you have a path from A to V, where A is the starting node. Okay, now I want to say, if a node U is reachable, there is a path to it from A. There's a sequence of edges, A to V1, V1 to V2, V2 to V3, and so on, where you eventually get to U. Okay? Now, what we're going to do is we're going to say, assume it's not found. Right? Okay, so what happens is we have some sequence of edges, A to something, to something, to something, to something, to some vertex Z, and there's an edge from Z to W, and then there's more edges, and then you get to U. Right? That's the picture. That's what we get to assume, because it's reachable. Reachable means there's a sequence of edges that take you from A to U. Okay? So now we're going to say U, this vertex U is not found. Okay? So when you go back here, some of these vertices are found. For example, A is certainly found. We start with A. Right? That's how we start our procedure. We explore A. Okay? But somewhere along this path, one of these vertices will not be found. Right? The first one that's not found is somewhere in here in the middle. Because you go from A, they can't all be found, because then you would have found U. So there's some first vertex along this path which was not found. Right? And we'll call that one W. Z is, and we'll say, now all of these were found by the algorithm. Right? They all were explored. So Z was explored. Okay, so W is the first one that's not found, and Z is found. Okay? Okay, now you see why W must be found? Well, right? Do we see why W must be found? We have to look back at our program, right? We're arguing our program is correct. Okay, so now look at the program. What does found mean? It means we called Explorer on Z. Okay, if we called Explorer on Z, look at this loop, lines 2 and 3. Right? If we called Explorer on Z, what we do is for each of its edges, if the other end is not marked, we would explore them. Right? So what we would do is we'd look at the edge, Z to W, we'd see that W is not marked, and then we would explore it. Okay, which is a contradiction. Okay? Okay, explore Z, the call that has Z as its argument would have to call explore W if W was not already found. Okay? So therefore we do call explore on W. Okay? Okay, so that's the proof that it does get there, right? And you see that it's connected to the code, connected to the description of the algorithm. Right? We're really looking at the text of the code and saying what happens. Right? Okay. Okay, so the point is that's an inductive proof. Does everybody see that's an inductive proof? Okay. So why is it an inductive proof? So it's this in 70 you do the smallest counterexample is doesn't exist. That's induction. So that's what we did. Okay? And here's how we do it. Okay? So we're going to find the smallest k path length where the property doesn't hold. So there's some length of paths from A to Z. It has some length. Let's say it's k. Okay? Or A to W. It's k. So now we're saying that this path of length k from A to W, we didn't actually explore W. For any path less than k, we did explore it. So this is the smallest example. So it does hold. So where the property doesn't hold. So say whatever k minus 1 is the length to Z. So we know that Z is explored by induction. Okay? And then we say, well, so must W be. Right? Because explorer of Z would call explorer of W. Okay? So it does hold. So in fact, the property does hold for W. The property being that it is explored. Okay? So every node is explored. Let's look at the shortest path where some node is not explored. Oh, by the way, the predecessor was explored, so this one is also explored. So that's a contradiction. There is no smallest k where this property doesn't hold. Okay? So it must hold for every k, and that's the proof. That is an inductive proof. Essentially, almost all our proofs are somehow induction. Okay? So now, finally, we want to do the running time analysis. Okay? So let's see how we're doing on time. Oh, okay. Okay, so there's recursive call, right? How are we supposed to analyze recursive things? How have we done it? We're not supposed to do it for this thing. But how do you analyze this, right? Do you see we could write a recurrence? You see, because we're calling explore on W, right? You can say T of n is equal to T of, n minus 1 or something, right? Okay, so there's actually two parameters here, n and the number of edges. So, in some sense it's D, T of D, because this thing goes all over its neighbors, right? This loop here goes all over its neighbors, times a recursive call to this W, right? Plus order D, because you look at every edge. Okay, so that's a valid recurrence. Okay, it is valid, right? Because you won't ever explore V again. Okay, but this is an exponential. This is a valid recurrence, but it gets useless. It gives you the bound on this will be exponential. It'll be like d to the n, right? You can see that you keep multiplying by d, and this only goes down by 1. This is a disaster. Now that's not how long the algorithm takes. Yeah, d is a degree, the max degree of any node. The d is the max degree of any node. He asked what is d, and here we're not going to use it, but I'm just saying this is not something you should apply a recursive algorithm to. You have to do a different style of analysis to analyze the runtime. Okay? Okay. I mean, you can. The technical term is terrible, it gives you a terrible bound, right? So, or exponential. That's also a terrible thing. And it's not really, it doesn't really take that long, right? We saw it was very efficient. Okay? You saw the algorithm run. It basically, what did it do? It sort of touched everything once. Right? That's what it did. Okay? So that by itself, that now you know how long it takes. It's linear in the size of the data structure. Because it sort of only touched everything once. Does that make sense? Or once or twice. Every piece of the data structure, right? That's what happened. If you looked at a node, you never looked at it again. If you looked at an edge, how many times might you look at an edge? Well, how do you look at an edge? Let's look at this. What we do is we go over the adjacency list for each edge, V, W, and E. That's pulling the adjacencies, all the neighbors of you. Okay? So you're looking at the adjacency lists. And for each element of the adjacency list, you call an explorer. But you do it or not. You at least go through this loop for each element of the adjacency list. Now, how many adjacency lists is each edge on? How many adjacency lists is each edge on? It's on V's adjacency list and W's. So exactly 2. Okay? So the running time of this algorithm more or less is just the total size of your adjacency list, which is twice the number of edges. Right? This is why I asked this question way back. Okay? So let's see. But now I did it in words, but I want you to have it, see it, think about it a couple of times. So, okay, how to analyze. N is the number. I always use N and M. The book tends to use the size of V for the number of edges. What is going on? Okay. Charging work to something. Okay? Because it's not really, that recursive thing was a gross upper bound, because we're not always calling the explorer on all of our neighbors, right? That's why it was a gross upper bound. Okay? So for node X, you explore it once, right? If you never call explorer on any vertex more than once, right? Because if it was visited, if it's not visited, then you can call explorer on it. You never will do it again. Okay? And then what do? You go through, you set visited to true. That's the first thing you do. So you never get called, explorer never gets called on you again. That's the first step. You write the chalk. And then you go through this loop. And what does this loop do? It processes your adjacency list, all the incident edges. Okay? Now, each edge is processed twice, right? So now what's the total work? This is the total amount of processing you do. Okay? So each edge is processed twice, because how many adjacency lists does it appear in? 2. Right? U's adjacency list and V's. W. Or V and W's. Okay? So there's order n time that you need to explore each vertex. Right? And then order m time to process each edge twice. Okay? And that's the total time. Okay? So you make an argument. You don't just write down a recurrence. You're like, oh, look, what is all the work I'm doing? Okay? So you really sort of, okay. So you're, okay, yeah, so good. So let me go over this. So I'm going to ask some people, even though I'm doing the summary slide and people seem to hate summary slides, wait till the end so that other people can listen. Okay, I'll go fast. FFT wrap-up, this is what I said before. Okay, so now you should test yourself and you should see if this is more clear to you. Or at least understand what you have a responsibility to understand. Okay? Okay, and this is it. The basic idea is you break up the polynomial into 2 polynomials, the odd and the even, and you evaluate those polynomials on the squares of the points. And how many points, and we choose a set of points carefully so that the squares of the points will always be half as many points as the points themselves. Okay? Graphs, we have these matrix representations, which you've seen before, and we did this analysis of Explorer. Okay? And so there you see the property of the stack, and you already get a hint that it's giving you structure about the graph. It divides the edges into 2 groups, the tree edges and the non-tree edges, which have a specific way of interacting. They're between a descendant and an ancestor in the tree. And then finally, how do you do the running time out? This is a little obsessive, but it's like that song, Every Little Move She Makes. You just have to obsess about what the algorithm is doing. And you have to charge for every piece of work it does. And you just have to account for it. And that's what we did. We looked at the algorithm. We said it processes the adjacency list once. Every one of them. So the total runtime is the total size of the adjacency list. Okay? Thank you.
In the book, the 2.6 section on FFT is very long. Should we know the entire 2.6 section?
That's FFT?
Yeah.
Probably.
Okay.
I mean,